In this lecture, we will discuss complex numbers and its algebraic operations. First, let me recall basic number system which we are familiar. Natural number system which we are familiar from our childhood, which is denoted as 1, 2, 3 and so on, and set of integers which contains the natural numbers including 0 and the negative numbers as well as the positive integers. And what we encounter is the division is not possible just using the set of integers. So, we end up constructing rationals which is defined by p by q, where p is coming from integers, q is coming from natural numbers, and we can interpret each number in the rational numbers as a point on a line which is distance from a 0. Okay. One can be thought as it is placed after 0 with a unit step. Similarly, 2 is placed with the distance of 2 units, and minus 1 is behind 1 unit to 0, and similarly try to fill the other fractions. Then we can place the rationals as a number which is gives a distance from a 0, we can say place on the line. Our question is whether this rational number system completely fills this line, and the answer is no. There are lots of gap in this rational number system. Let me explain with a simple example. Consider a triangle, right angle triangle with sides having unit length. Then by Pythagoras theorem, the distance here d gives that d square equal to 2. Our question is, does there exist a rational number? So, our question here, whether does there exist a rational number whose square is 2. Let me write this question. Does there exist a rational number, let us call it as p by q in q, such that p square by q square equal to 2. The same question can be rephrased as, in other words, is the polynomial which is x square minus 2 as a root in Q. Okay. So, the answer is no. Let us see a simple proof. For this, we go proof by contradiction, that is, you assume that there is a rational number satisfying this equation, then we arrive a contradiction. So, let us start. Suppose there is a rational which is p by q in q. So, any number when we are considering from the rational number, it is of the form p by q with no common divisor, that is the p by q with the GCD which is just 1. So, the greatest common divisor only possibility is 1, which satisfies such that p square by q square equal to 2. once we see this equation, immediately we see that p square must be even. So, this equation meaning is that it is p square equal to 2 q square. This immediately implies that p square is even number, and then we can conclude that p must be even, p is even. Why? Suppose it is odd, then p square must be odd. So, which immediately gives the contradiction. So, we get the result p must be even. So, once p is even, what it means? P can be written as 2 times k for some k in integer. Now, substitute this one in the equation, let us say 1. Okay. So, what do we get is, so from 1 we get q square is 2 times k square. Again the similar argument, we can conclude that q is even. Now, do you see the contradiction? We see that p and q now as at least the greatest common divisor as 2, but we started with there is no greatest common divisor, which is contradiction. Now, let us conclude what we derived. Conclusion: there does not exist, there is no rational, let us say R in Q, such that R square equal to 2. In other words, the polynomial or the polynomial x square minus 2 has no roots in Q. And now, the real number system, which is the one which fills this gap in the rationals. So, what we encountered in the rational number system, lots of gap, which namely that we found a distance on this triangle which is not represented by the rational. So, the real number system, the one which fills this gap. So, let me write it as the set of real number system which completes the rational numbers. Which is denoted as R, that is the set of real numbers. Now, again the question is, are we happy with this real number system? No. Let us say why. So, suppose I ask, is every quadratic polynomial has a root in real numbers? Let us pose this question. So, question is every polynomial let me make it as quadratic polynomial, every quadratic polynomial has a root in R. Okay. Answer is no. So, let us see the example. Consider the quadratic polynomial, simple one, x square plus 1. Okay. Whether it has a root in real number system? No. Let us see the argument. For every element in the real numbers, x into x, that is our x square is always non-negative. This can be just realized as, maybe let us say x is negative element, we know that negative multiplied by negative is positive, again positive multiplied by positive, again it is positive. So, we observe that x square is always non-negative, thus immediately implies that x square plus 1 always greater than or equal to 1. So, which means that there does not exist any, say there does not exist a alpha in R such that whose square is minus 1. Okay. So, we observe that there is no real number whose square achieves the minus 1. So, this is the place we introduce the imaginary number which achieves this. So, that is we called as number I. So, we introduce imaginary number I such that whose square is minus 1, and we mean this way, say I as square root of minus 1. Okay. Let me again repeat, we are not able to find any real number whose square is minus 1. So, in that way there is nothing a real number achieves this. So, you associate a imaginary number whose square is minus 1. In this way the complex number has been introduced. So, let me define what is the complex numbers. Complex numbers, it is denoted as the C, which is defined as a number, it is of the form a plus I b, where this I for the imaginary number, that is I square is minus 1, such that a and b comes from the real numbers. Okay. So, let us see what is this element. Simple example, it is customary that we usually use Z to denote the complex numbers, and if you consider any a b comes from real numbers, let us see that suppose say a equal to 2 and b equal to 3, this is a complex number, and something which is root 2 plus I, let us say root 7, or z equal to something minus pi plus some e to the power pi. So, by definition a complex number, it means that a plus I b, where a and b are from real numbers. So, by the definition what we attempt to see is that it can be visualized as ordered pair a b, okay. That is each complex number a plus I b we can think as ordered pair a comma b. So, before going to that, let me just define when do you say two complex numbers are equal, then it will be very easy to associate with the ordered pair. So, two complex numbers Z1, let us call it as a plus I b, and Z2 is c plus I d, where a, b, c, d all from real numbers. So, we say that two numbers are equal, that is we are saying Z1 equal to Z2 if and only if a equal to c and b must be equal to d. So, the component wise if they are equal, then the two complex numbers are equal. With this definition we are immediately see that each complex number can be associated to a ordered pair in the R cross R, that is, so for each z in the complex numbers, it is of the form a plus I b, where a and b from the real numbers, and what do we see is that the a plus I b we can associate it to a ordered pair a comma b, which is element in R cross R, that is a Cartesian product of real number system. And similarly, given a ordered pair a b, we can associate a complex number. So, what do we see is that there is a one to one correspondent between complex number system to the real number, say to the R 2. Okay. So, in this way we are able to see the complex numbers, which is not really an imaginary one. Now, we are really able to see that it is associated to the number in the plane. Let me just draw a picture. So, what do we see here is, so with this association I see that, say a number here, let us call it as, say z1 is 1 plus I0. By this association it is 1 comma 0, and what we see here, it is I is z2 equal to 0 plus I1, which is 0 comma 1. Now, we are seeing that for each number we are able to identify one point in the plane. Now, very naturally we see that the real number, okay, this can be treated as the real line or real axis, and the y axis will be treated as imaginary line. That is basically what I am trying to do is, I am trying to identify each complex number on the plane. So, let me introduce further notations, then it will be easy to visualize. So, we are going to write 0 plus I0 as just 0 and 1 plus I0 as just 1, and in general any real number just I times of 0 we are going to just write it as a, and similarly a plus. So, similarly the 0 plus I1 is just the I, and 0 plus IB we are just going to write IB. Okay. So, what we know is the number 0 plus I0, which is corresponds to 0 comma 0, and this point corresponds to 1 comma 0, and similarly this corresponds to a comma 0 in the plane R2. So, which means here when I write IB, it corresponds to the point thus. So, what you see is that this imaginary line, this can be associated as unit I, and here what you have the real line with unit 1, and if I take a point here which is 1 comma 1, that is 1 plus I. Okay. So, what we are trying to say justify here is, so I is now is no more an imaginary number, we are able to associate one point in the R2. Okay. In this way we have a realization for now complex numbers. Let us introduce some basic algebraic operations on complex numbers. So, first let us introduce the addition. So, let us consider the two complex numbers z1 z2. Let z1 z2 be complex numbers, that is, say let us call it as z1 is a plus ib and z2 is c plus id. Then the addition z1 plus z2 is defined as component wise addition, that is a plus c plus I b plus d. Okay. So, with the previous identification to the R 2, the complex number can be identified in the R 2, then let us just see with the simple example. Let us say I would like to add the complex number 1 and another complex number I by definition. So, let us just consider example z 1 is 1, which means it is 1 plus I 0, and z 2 is 0 plus I 1. So, the addition gives us component wise addition, that is 1 plus 0 and 0 plus 1, which basically we get 1 plus I. So, let us just try to identify what is happening here. We are visualizing in the point in R 2, this can be thought as a vector. Okay. It is from the 0 to 1, it is a vector, and similarly I is a vector. What is this addition does? So, vector can be just say identified as its direction and the magnitude. In this way, what I can see is that I can basically visualize this is another vector which basically represents this, the unit length 1. Okay. So, the addition here from this vector plus this, I basically like I am just try to imagine you are displacing something. Okay. You started from the 0, you basically displayed to I, and then further you displace to this point. This point is 1 comma 1, which basically gives 1 plus I. Same thing basically you could see that, you could see the other way, that is you go from 0 to 1 and further the parallel 1, the same vector here, which basically achieves this, which means this operation is commutative. Okay. So, the addition, it has a meaning, physical meaning. It is trying to associate that when we are adding two vectors, it basically gives the corresponding displacement for the associated vector. So, let us see the properties of this addition operation. So, first one, we already saw that by definition itself it is closed. So, it is closure law, that is when we add two complex number, by definition it becomes complex number. Okay. So, it is closed and with respect to this addition operation. Second, associative law, it says that you first add z 2 z 3, you get a complex number, and then add with z 1, then this is same as first you add z 1 z 2, you get a complex number, then you add with z 3, and the resultant one are equal for every z 1 z 2 z 3 in the complex numbers. So, whatever we have written, this is verifiable, that you consider 3 complex numbers, then you verify this operation, that it satisfies the associative law. Third one is commutative. Z 1 plus Z 2, which is same as Z 2 plus Z 1 for every Z 1 Z 2 in complex numbers. Fourth one, identity element exists with respect to this operation, that is say the. So, what we need is when we consider a complex number, you add something, we need to get back the same element. Because of commutative relation, we no need to write the 0 plus again this. So, here we found that 0 is the identity element with respect to this plus operation. So, that is what we are seeing is you take any complex number a plus I b, we know what is the meaning of 0 element, it is 0 plus I 0, we know the addition, here addition is component wise, then a plus 0 plus I b plus 0. 0 is the identity element in real numbers with respect to plus operation. By a result we get that again it is a plus I b. This is for every z in complex numbers, and the inverse with respect to this plus operation we get the minus z as the inverse element, that is say where, so if z is a plus I b, where minus z denotes minus a plus I minus b. So, when we sum these two elements we get the 0 element, that is the identity. So, for every z in the complex numbers. So, let me again repeat, we introduce the addition operation in the set of complex numbers, and then one can verify that it satisfies these 5 laws. Okay. So, once it satisfies this 5 laws, then it is called commutative group with respect to this plus operation. Now, some simple observations. When we add two complex numbers, let us just consider say z plus z itself. Let me consider a general element a plus I b and again a plus I b. What we get is 2 times of a plus 2 times of b. Now, meaningful if this is comes as 2 times of a plus I b. Okay. You need to understand here this we have not defined it. Okay. So, when you are basically multiplying 2 times this, 2 is again a complex number 2 plus I 0, product with this we have not defined it. So, this is our natural interest. Okay. That is, when you are having a vector, you are adding 2 vectors, same vectors, which basically like only the magnitude will increase in physically, that is what we will expect. Okay. So, now with keeping in this mind, we would like to define a product on the complex number system. So, let us see how the product operation to be defined. I consider say a plus I b product with c plus I d, if suppose we are defining it okay, component wise like how we do it in the addition. Okay. Suppose I do it a times c plus b times d, I can write this way as well because it is commutative. So, what we encounter immediately that the above relation is not satisfied, which we are interested, that is the 2 can be written as 2 plus I 0 product with this a plus I b. If I consider this as my product operation, then I end up which is component wise 2a plus I 0, because in real number 0 multiplied by a real number we get 0. So, which is not really our say interest. So, and one more fact, our interest to get something which is I square equal to minus 1. If you remember, our original interest is I square must be minus 1. Try to write down what is this I. I stands for I 1 and then product with, thus it should achieve that minus 1 plus I 0. So, keeping in this mind, we would like to define a product operation. Let me first define the product operation which achieves our basic need. So, if you consider say Z1 as a plus I b and Z2 as c plus I d, product of Z1 Z2 as defined as, let me again just write these elements, C plus ID, which is defined as AC minus BD plus I times AD plus BC. So, again this is a definition. Okay. So, when you consider two complex numbers, we define the product in this manner because we do not know what is the interaction of say IB with the other object, but we know the product in the real number system. So, using product in the real number system, we are just defining this operation. So, which means this AC minus BD is a real number plus I times another real number, this is a complex number. Okay. Now, question is whether it satisfies what we basically interested. For example, that is I square, whether it is minus 1 with respect to this product. So, when I consider I, so I take Z1 as I, Z2 as I. So, we see that Z1 to Z2, which is 0 plus I1 and 0 plus I1, which gives that A multiplied with C, that is 0, and then minus B multiplied with D, that gives minus 1, and the other part similarly A is 0 multiplied with D is 0. So, the rest of the fact here we get it as 0. As we agreed, the notation for this one is minus 1. So, what we encounter here is I square is minus 1, and similarly if you are multiplying by a scalar, like suppose I consider Z1 as alpha, any real number. So, where alpha is a real number. So, which means what we have, this is alpha plus I 0 and Z2, which is some general complex number. Then the multiplication here, what we have Z1 dot Z2, we see that A multiplied by C, that is alpha A plus, and the next factor involves with the B times D, that is 0 and plus I times the next factor A multiplied by D, that is alpha B plus again another factor which is B multiplied with the C, that is 0. So, we get that it is just when we are multiplying by a scalar, we are getting scalar times of the vector. So, in this sense we really see that this is just the, so left hand side is nothing but the alpha times A plus I B. So, with this product we are able to achieve our desired interest. Let us see some more examples with respect to this product. So, let us try to imagine what is happening with respect to this product. I take 1, suppose I multiply by I. So, with respect to this complex number, so I take 1 and then multiplying I. So, one can verify that it gives again I. So, what is the meaning of this? This is 1 plus I 0 multiplied by 0 plus I. One can verify that it gives 0 plus I. Okay. So, we are getting I if I multiply 1 with I. Again if I multiply I with I, we are getting minus 1, and similarly if I multiply I again, we get a minus I. So, what is happening? We observe that we are rotating this vector, the unit vector, we are rotating to this particular, it reaches the I, okay, when we are multiplying by I. Similarly, when I multiply by I with this vector, again it is rotated by a angle of 90 degree. Similarly, if I multiply I with minus 1, we get this. So, if you recall, when we are considering a real number whose square we are not able to achieve -1, but with this complex numbers product we are able to get that I square is -1. So, what is the freedom we have given here? The freedom here is we are introducing in the multiplication the rotation concept, okay. So, which we are not able to do in the real line. When you are multiplying, when you are taking a square of a number, either it basically stretches or shrinks, okay. So, but now what we observe is we are adding one more factor, that is rotation. By doing 2 times of transformation, 2 times rotation, we are able to get the -1. So, let us observe with the general vector. Suppose I consider say a vector which is, so I am not able to exactly plot for 45°, but just imagine this point is 1 plus I, and suppose I consider say another vector. So, from here it is a straight line, that is y equal to x, we get 1 comma 1. So, the angle we know that is 45°. So, this one is 45°. Similarly, you take a line which is y equal to minus x, you hit the point with the 1 minus I, which is again 45° angle. Now, let us try to multiply these two numbers. So, 1 plus I multiplied by 1 minus I. So, we observe that this is say a b, that is 1, and the other factor which is plus 1, and then plus I times, we need to multiply it with the a. So, this is minus 1 plus 1. So, basically what we see is that just 2. So, let us see what is the point we got 2. So, what is the explanation? So, we fix the real line and see what is the angle for this vector with the real axis, that is 45°, and then similarly the same thing. So, if you try to measure the angle for this vector, let us call it as the alpha, and let us call this is something which is beta. Once I multiply, it adds this angle, okay. So, once I multiply, I reach the vector which is 2, it is magnified, okay. So, what we are seeing is the multiplication has a physical meaning, that it involves with the rotation concept. Let us see that what are the properties of this multiplication, which we are going to again verify the group axioms, that is the closure property. So, when I multiply two complex numbers, I get again the complex number for every z1 z2 in the complex number. Associative law. So, multiply z1 for the with the product, that first take the z2 z3 product, you get a complex number, then multiply with z1, which is same as first multiply z1 z2 and then take the product with z3 for every z1 z2 z3 from the complex number. This identity satisfies. Commutative law. Which is z1 multiplied with z2, which is same as z2 multiplied with z1. Again this is for every z1 z2 in the complex numbers. Identity. So, there exists a number which is nothing but the 1, you multiply any number with 1, we get back 1. Here 1 basically denotes, where as you remember in the notation, this is 1 plus I 0 for every z in the complex numbers. Inverse, it is interesting that though the product is complicated, for each non-zero element there exists a complex number which we are calling it as z inverse, such that z multiplied by z inverse gives identity element 1. So, this is true for every non-zero, for every z in complex numbers which is non-zero. So, let us see whether the existence of z inverse. So, we are demanding z inverse must be complex number, which means that it is of the form alpha plus I beta. So, we intend to find what is this alpha and beta. So, a plus I b multiplied by alpha plus I beta, which is I plus 1 plus I 0, and the product here it is a alpha minus b beta, that must be equal to 1, because the component of the real part equal to 1 and a beta and alpha b, that is equal to 0. By solving this equation for alpha and b, we get the value for alpha and beta. It is easy to see that. So, let me write the equation again. So, we are like to solve this equation, a alpha minus b beta equal to 1 and a beta plus alpha b, this is equal to 0. So, by multiplying say with the first equation, we can multiply by we can first solve for alpha. So, we can create the common factor for beta in the two equation by multiplying here a and here we can multiply by b. Then what you see is that the once you add these two equation after multiplying these two factors, we get here a square alpha plus b square alpha, that is equal to a. So, alpha is a by a square b square. Similarly, we can calculate beta, which we get it as minus b by a square b square. So, the z inverse. So, note that where did we use z is non-zero. Okay. So, we are dividing here by a square plus b square, which is the factor comes from the z. So, since say z is non-zero, it means that one of the either a or b is non-zero, that implies that a square plus b square is non-zero. So, the divisible makes sense. So, z inverse, which gives a plus a square plus b square plus I times minus b by a square plus b square. Let us calculate a z inverse. Say let us do some example. When I take say z as I, so the z inverse by definition, what do we get? It is 0 by 1 plus I times minus 1 times thus. So, we see that it is I multiplied thus, which we are basically notation wise we use minus I. and let us do one more example. Z inverse is 1 by 2 plus I times minus 1 by 2. So, what are the group operations we have mentioned now? Let me just recall. So, we have say mentioned that closure law, associative law, commutative law, identities exist, inverses exist for every non-zero element. In addition to this, there is a nice interaction between plus operation and the multiplication operation, that is explained through the distributive law. So, first say add the complex numbers Z2, Z3, then you multiply by Z1, which is same as first multiply Z1 to Z2 and then Z1 into Z3, then you sum these two complex numbers, both are equal, and similarly when you have Z1 plus Z2 Z3, what you have is that Z1 Z3 plus Z2 Z3 for every Z1 Z2 Z3 in the complex numbers. So, we can verify for given 3 complex numbers the multiplication and the addition, it is compatible in this particular sense. Okay. So, once a number system satisfies that it is a group, abelian group with respect to plus operation and multiplication with respect to the our product operation, and together with the distributive law, it is called field. Okay. C is called field. Now, let us see calculate products of I, that is power of I. So, when we are considering I power 1, it is obvious, that is I itself, and I square we can write it as I to I, which is our minus 1, and I cube can be written as I square multiplied by I square is minus 1, and so we get here minus I to the power 4, we get 1. Okay. Now, we can increase the power. So, I to the power 5, this can be factored as I to the power 4 product with I, which gets I again, and I to the power 6 we are getting minus 1, I to the power 7 which is minus I to the power 8 we get 1. Now, by induction we can verify that it is I to the power 4k plus 1 is I, and I to the power 4k plus 2 is minus 1, and I to the power 4k plus 3 is minus I, and I to the power 4k is 1 for every k from 0, 1, 2 and so on. Okay. So, by mathematical induction you can verify that it satisfies this. So, from this particular identity what we can see is that a simple problem that we can see that sum of k equal to, say you can take any say number, let us say simplest one, let us say 10, I consider I to the power 4k plus 1 plus I to the power 4k plus 2 plus I to the power 4k plus 3 plus I to the power 4k what do you get? The answer is 0. So, from the above expression, when you sum up these terms, we have 1 together minus 1, and similarly I with minus I. So, the sum here, so what we know is from the above identity, this is I and this is minus 1 and this is minus I and plus 1. So, the sum is 0. So, for you exercises, just find the what is the sum, I to the power k plus I to the power k plus 1. And a warning example, we cannot say this, that is square root of a b is equal to square root of a product with this. This is need not be case for the complex numbers. Simple example, you consider a equal to minus 1, b equal to minus 1, then we see that square root of the left hand side is square root of minus 1 product with this, which is square root of 1, which is 1, and the right hand side we see that square root of minus 1, we have I to I, this gets minus 1. So, in general the square root of a b need not be equal to square root of a product with square root of b. With this we conclude the basic operations in the complex numbers. In the next lecture we will discuss organ plane and its representation. Thank you.